In this lesson, we're going to go over how to graph square roots, and then we'll be able to identify features of the graphs. So if you could label this graphing square roots. So the parent function, or what is the most basic type of square root function, is the function f of x equals the square root of x. So all the other square root functions are just transformations of the square root of x function. So some of them might be moved up, down, left, right, stretched, or compressed. And we saw those transformations before. But the focus of this video is just to understand, what do these square root functions look like? So let's start off by looking at the parent function. So we have f of x equals the square root of x. Remember, that's the parent function, or the most basic function of the square root function family. So when we graph, you may be able to use your calculator, but sometimes they will ask you to use a table. So let's look at what this looks like with a table. So basically with a table is they'll give you the x value. So for example, they give you x equals 0 here, and you need to plug that into your function. So when I plug 0 in for x, I'm going to get f of 0 equals the square root of 0, which is 0. And then I would move on to the next one. So then I would plug in 1. F of 1, the square root of 1 is 1. For 4, f of 4, square root of 4 is 2. The last one, f of 9. So square root of 9 is 3. So this is your table. And then you're just going to plot. So these are going to be ordered pairs. So this would be the ordered pair. So the first one would be the ordered pair 0, 0. The second one would be the ordered pair 1, 1. Then the ordered pair 4, 2. And then the ordered pair 9, 3. So these are your ordered pairs. So go ahead and take a minute and plot those. So you plot them, and then when you unpause, I'll have plotted them as well. So hopefully you took a minute and graphed that. This is, if you did, this is sort of the graph that you should have came up with. This is what the square root parent function looks like. So let's go ahead and identify the key features of this graph. So for the key features on this graph, we have, starting with the vertex. The vertex, this is the starting point of your graph. So this is my vertex. It's at the ordered pair 0, 0. This is sort of where my graph starts. It's the end that doesn't have the arrow. You can think of it that way. The domain. So if we look, remember, domain has to do with x values. So if we look at our x-axis, so if we start at our starting point, at our vertex, notice all the x's go to the right. Nothing on my graph goes to the left. So that means I'm starting at 0, that's the x value of my vertex, and I'm going all the way to infinity. I'm going all the way to the right. The range is similar, but remember, range again has to do with y values. So if I start again at my vertex, notice my graph goes above my vertex. All these points that I'm putting here, these purple dots, are points in my graph. Those are all above the vertex, which means my y values are all above the vertex. They're all above that y value of 0. So it's going to be 0 all the way to infinity, because they're all above the vertex. The x and y-intercept both happen to be the origin. So here's my x-axis, and here's my origin. And then here's my y-axis, and this is my origin. So notice, in this case, it just happens that my origin is a point on the graph, so this is my x and y-intercept. And then end behavior. As x approaches infinity, what happens to y? So remember, this is just saying, look at the right arrow. Remember, if your right arrow is going up, it means your y values are increasing. And this arrow, while it's a little hard to tell because it doesn't go up very fast, this arrow is going up. So we would say as x approaches infinity, y approaches infinity. Again, like I said, it's not going up very fast, but it is going up. So the y values are increasing as x gets larger. So these are the key features of the square root parent function. So before we get into graphing, I do want to point out that there's two ways that we can find the domain of square root functions. The first is by graphing, which we saw in the parent function. The second is we could use algebra. So we are working with a restricted domain, so we won't be able to use the whole x-axis. So what we can do is we can set what's under the radical. We can set that greater than or equal to 0, and then solve for x, and that will help us find the domain. So let me show you an example of that. So I just want to find the domain. I don't want to graph this or anything just yet. I just want to find the domain. So I have f of x equals the square root of 2x plus 3. So I want to find the domain. So I'm going to take what's under the radical. So I'm going to take 2x plus 3, and I'm going to set it greater than or equal to 0. And now I'm going to solve it. So I'm going to draw the line. I'll get rid of the 3. This gets me 2x is greater than or equal to negative 3. And then divide both sides by negative 2. So I get x is greater than or equal to negative 3 halves. So my domain is x is greater than or equal to negative 3 halves. If we want to write that in interval notation, this means that all my x's are larger than negative 3 halves. So I could write negative 3 halves to infinity. So either notation is fine. For the range, we are just going to use graphing to find the range. So now let's look at some examples. So example 1, graph and identify the key features. So I have f of x equals the square root of x minus 3 plus 1. So I provided you with a table, and I got you started on the first one. So when x is 3, I provided you with your x values. When x is 3, you're going to plug in 3 for x. So I showed all the simplification there. So when you do that, you get 3 minus 3, which is 0. Square root of 0 is 0. So 0 plus 1 is just 1. So I have f of 3 equals 1. So my order pair is 3, 1. For 4, I'm going to do something similar. I'm going to do f of 4 equals the square root of 4 minus 1. Sorry, 4 minus 3 plus 1. And if you do that simplification in your calculator, you would get that this is 2. So this is the order pair 4, 2. F of 7, same idea. So we'll do square root of 7 minus 3 plus 1. So this would be square root of 4 plus 1, which is 2 plus 1, which is 3. So here I would have your pair 7, 3. So I'm going to take and I'm just going to plot each of these. So go ahead and plot them. Pause the video. I'm going to plot them. When you unpause it, I will have plotted these. So this is the graph that I have for example 1. So make sure yours looks like mine. And let's go ahead and identify the key features of this graph. So remember the vertex, this is like your starting point. This is the part that doesn't have the arrow. So this is right here. And to identify the vertex, we'll write it as an ordered pair. It's going to be 3. The x value is 3. And the y coordinate is 1. So my vertex is 3, 1. The next part is the domain. So you can look at the graph and find the domain, or you can set what's underneath the radical greater than or equal to 0. So I'm just going to show that way. So x minus 3 is greater than or equal to 0. And then solve. So add 3 to both sides. So I get x is greater than or equal to 3. So you could write this as your answer, or you could write your answer as 3 to infinity, because it says greater than or equal to, which means all my other x's are greater than 3. Or you could have got that from the graph. So if you looked at, here's your starting point, notice all your other x values go to the right. So 3 to infinity is how you would get that from the graph. For the range, it's going to be the same idea. You're going to start at your starting point. So the y coordinate of your starting point is 1. So I know I'm going to have a 1 in my range because that's where my graph starts. Notice my graph goes above this dot. That means my range is going to go 1 to infinity. And I'm going to put a bracket around 1 because my purple line was above my starting point. The x-intercept and y-intercept, there doesn't happen to be an x or y-intercept because this graph never touches Here's the x-axis. My purple graph never touches that. And here's the y-axis. Again, my purple graph never touches that. So for both of these, there is none. Then end behavior. So as x approaches infinity, meaning as your x's get larger, what happens to your y's? So again, you're just going to look at the right arrow there. That right arrow, remember, this isn't going to go climb very steeply. Doesn't look like it's pointing up, but this is really pointing up. It's just not climbing very steeply for you to see it, but that arrow would be pointing up. So as x's get larger, y's get larger as well. So example 2, graph and identify the key features. So we have f of x equals negative square root of x plus 2. So I went ahead and I gave you the x values, and then you needed to find the y values. So when x is 0, when I plug 0 into this equation, I get negative square root of 0 plus 2. Well, the square root of 0 is 0. So I'd have 0 plus 2, which is just 2. So my ordered pair here is 0, 2. So why don't you go ahead and find the other ordered pairs, pause the video, find the other ordered pairs, and plot them. When you unpause it, you'll see the graph there. So hopefully you were able to graph it, and your graph should look something like this. There's my ordered pairs, and there's my graph. So the key features, starting with the vertex. Again, the vertex is your starting point. So my vertex is right here. This vertex has an x value of 0 and a y value of 2. So this is my vertex, 0, 2. So number 2, the domain. So again, we could set what's underneath the radical, greater than or equal to 0. So x is greater than or equal to 0. So this would be one way, and this is already solved because I got x by itself. So x is greater than or equal to 0. Or you could look at the graph. So if we start here, notice my graph goes to the right. This goes down and to the right. So that means all my x values are larger than my starting point because I go to the right. So this would be 0 to infinity, include a bracket around 0. That value is included. And then the range. So for the range, again, you're looking at your starting point. Here's your starting point. This is what's the y value of your starting point? This has a y value of 2. So I know my range is going to have a 2 in it because that's a starting point. And then notice my graph, all the points go below 2. So that means all my y values are less than 2 since all my points lie below 2. So when we write our range, that means, remember, we write smallest to largest. So I'm going to write negative infinity to 2 and put a bracket around 2. So just keep in mind when you're writing the range, you need to write the smallest y to the largest y. So 2 is the largest y value. So this vertex would be like a maximum point. The x-intercept, remember, that's where the graph crosses the x-axis. So here's my x-axis. The graph crosses right here. So this was the point 4, 0. The y-intercept, remember, that's where the graph crosses the y-axis. So here's my y-axis. And this is my y-intercept. This is the point 0, 2. So 0, 2. And then end behavior. So as x approaches infinity, y approaches what? So if we're looking at this arrow, you notice the graph is continually going down from the starting point. So since the graph is going down, that means this arrow is going down. Again, it's a little hard to tell, but this arrow would be going down because it's decreasing. Everything is below the vertex. So this would be going to negative infinity. So all my y values are getting smaller when I go to the right. Example 3. So you're going to try this one on your own. So graph and then identify the key features. So start off by completing your table and then plotting the points, and then you'll be able to do the key features part. So I want you to pause the video and give this one a try. When you unpause it, I'll have the work there for you. Hopefully you had a minute to work through this example. Here's what your graph should look like, and then here are the key features. Notice the vertex is at the point 2, 5. The domain is everything, all the x's greater than or equal to 2, so to everything to the right of your starting point. Or you could have said 2 to infinity using that interval notation. The range, 5 to infinity. So here's my starting point. All my y values are above my starting point. So I'm going to start at 5, and it's going to be everything greater. So it's going to be 5 to infinity. The x-intercept and y-intercept, this graph never touches either of those. Here's my x-axis. Here's my y-axis. My graph never touches either of those. So there is no x-intercept or y-intercept. And then M behavior as x approaches infinity. So meaning as my x's get larger, this arrow on my graph goes up. So this would be y goes to positive infinity. And so that's the solution for number 3. So there is an assignment in MathXL called Graphing Radicals, and you should be able to complete that assignment now.